All right, so we're on to acids and bases part 2. When we start to look at these situations, we want to kind of look at what does the solution look like. So last unit we talked a lot about solutions, and we had a lot of aqueous solutions that we were dealing with. So if I look at an aqueous solution of something that's an acid, okay, and so I'm going to say, let's deal with this as being hydrochloric acid. So if I throw in here, like say 5 molecules of hydrochloric acid into my solution, I'm going to get 5 hydrogen pieces, okay, and I'll get 5 hydroxide pieces. And remember that they're not really hydrogens floating around, they're really more that hydroniums, so it's the H3O+, but I like to just write it as hydrogens because it shows that I have those 2 different ions present. Now, if I, chlorine ions. There we go. So I have, for every one of these that go in, I'm going to get one of those and one of these. And that's where we look at our dissociations. So like hydrochloric acid will dissociate into forming hydrogen ions and chlorine ions. And so this is an aqueous solution, and this is an aqueous solution, and this is aqueous solution. And so we're looking at how many ions are we making. Now this is what we refer to again as a strong acid, because everything is going to dissociate fully. If we compared that to, again, something that would be like a strong base, okay, I'm going to have a new beaker here, and I'm going to put in there some water, because it's an aqueous solution. And we're going to add, this time we're going to add NaOH into it. So again, if I add 5 of those in there, I'm going to get 5 of the sodium, so some sodium ions present, and I'm going to get 5 of the OHs present. And so this is a situation that when we look at our dissociation of our sodium hydroxide, we're going to get sodium ions, and we're going to get our hydroxide ions. And this would be what we consider to be a strong base, because it's going to dissociate fully. Now, the reality is what happens when we take our 2 substances and we mix them together, okay? And this is where we're really getting into what happens during the reaction phase. So if I add hydrochloric acid to some sodium hydroxide, what's really going to happen here? And so if we write this out as a balanced chemical equation, we have our HCl. We're going to react that with some sodium hydroxide. We know that this reaction is going to go this direction, and it's going to act as a double replacement. So we spent some time learning about double replacement reactions. This is where the sodium is higher on the activity series than the hydrogen, so it's going to bump the hydrogen out. Okay, but that hydrogen ion is going to look for some place to go. It's going to attach itself to that hydroxide. So we're actually going to form some water, and we're going to make some NaCl. And so this is going to be aqueous in solution, and then this is really just a liquid. And so we see this as a reaction in which we had our aqueous solutions form some water and what we refer to as a salt. So these are salts. Now salts are just any ionic compound that would be in our solution that if we evaporated the water away, we would get those little crystals of salt. And so that's how we kind of go through and look at this. Now if we did this from what we were talking about in that complete and net ionic equations, we really have hydrogen ions that are floating around. We have some chlorine ions that are floating around. We have some sodium ions that are floating around. We have some hydroxide ions. that are floating around. All of this in our beaker container when we mix the two together. And then what happens then is we're going to take this guy right here and this guy right here to make our water. But these things are going to still remain as ions in solution. So the reality is these ions in solution are going to be our spectator ions. Those are the ones that are going to kind of be dropped out if we wrote our net ionic equation. And our net ionic equation then really comes out to be our equation that looks like water. And so this is where we see that shift in the pH happen, and we get a point to where we start to neutralize each other. So it's kind of like if we have something that's an acid but we add water to it, we can't ever make it not become a base until we add a base to it. But there's kind of a tipping point where we look at the relationship and we say that the hydrogen ions and the hydroxide ions become balanced. And this is what we refer to as neutralized. Alright, so become neutralized. And that's when we start to see that balance occur. Now we can look at that in a lot of different situations, but what we're going to do is look at it in some other type of reaction settings. So this is a double replacement reaction in which we're forming some water. So that's typical of a lot of our strong acid, strong base combinations that we would see this. In fact, most of our acid reactions with bases would form something like this, whether they're a strong acid or a weak acid, or a strong base or a weak base. If we go ahead, let's take a look at another type of a situation. This would be something like if we had a container that had some metal in it, and we added a solution that had some acid to it. So let's say we've got a beaker here again. And in the bottom of our beaker, we're going to put in, let's make sure that we're in an aqueous setting. We've got some hydrochloric acid. So we'll put in some HCl into this. And so I'm going to have my hydrogen pieces. Okay. And my chlorine pieces. Okay. So I've got a beaker that contains this. Then what I'm going to add to this is I'm going to add in some kind of a metal. So here's my piece of metal that I'm going to add into my beaker. Okay, so let's say I add in a piece of zinc. Now, what happens here is zinc, if we compare it on our green sheet to our activity series, zinc is higher on the activity series than the hydrogen is. So in this single replacement reaction, the zinc will bump the hydrogen and will form some hydrogen gas. So what we'll see here is we'll see a reaction in which our hydrochloric acid, which is aqueous in our solution, will react with our zinc, which is a solid in our beaker, and the reaction will take place to form some zinc chloride, which is going to remain aqueous in solution, and then it will form some hydrogen gas, which will bubble this out. So to balance this out, I'm just going to put a 2 there. There we go, we've got a balance. Now, again, in reality, when we look at this, we know that we've got some hydrogen ions that are going to be aqueous in our solution. Again, hydronium ions, hydrogen ions, same thing. And we're going to have some chlorine ions that are also going to be aqueous in our solution. Our zinc is going to remain as a solid in our solution, but then the reaction is going to take place and we're going to get zinc ions. And we're going to get some chlorine ions. And we're going to get our hydrogen gas. Okay? So now when we start to look at our spectator, the spectator in this case was that chlorine. The chlorine showed up as an ion in both situations. So what we really needed to know for our complete ionic equation is that if we have an acid present, something that can donate protons, okay, and we mix it together with some zinc, then we know that we're going to get some zinc ions and some hydrogen gas. And this is an example then of a single replacement of a metal with an acid. So the reality is, it didn't matter whether I used hydrochloric acid or I used sulfuric acid or I used carbonic acid or acetic acid, the base part of that acid really was not going to be something that I was going to be concerned about. So that's how we kind of go through and we look at it in the sense of what happens when it's a single replacement reaction with a metal. Now we can look at one other one too that we always like to kind of compare, and this would be anytime we have a carbonate. So if I have, say, a beaker again, make sure it's an aqueous solution, and we're going to have some kind of a, let's go again with our hydrochloric acid, so we'll have some hydrogen pieces present. Okay, and then what we're going to dump in here is going to be some sodium hydroxide, or excuse me, some sodium bicarbonate. So that's going to get dumped in here. Now the sodium bicarbonate, when it goes through, it's going to dissociate. So in other words, that sodium ion is going to go into an ion form, and that carbonate ion is going to be in there as well. But that carbonate ion is going to want to kind of react with the acid that's present. And we're going to get some bubbling and some fizzing. So this is like our baking soda mixed with an acid. So we would see this as a reaction where we have our hydrochloric acid again. We're going to add to that our NaHCO3, and we'll see this reaction take place where it's going to be like a double replacement reaction. The sodium is going to go together with chlorine. So we're going to make that salt. The hydrogen is going to join together with the bicarbonate, but that's going to form some water. So that's that neutralization that we tend to see. And we're going to get some bubbling and fizzing, and that's going to form carbon dioxide. And so this is a reaction where we're getting our carbon dioxide, we're getting our water, and we're getting our salt. Now again, if you start to look at this and think in terms of the aqueous and what ions are going to be present, so we're going to get aqueous situations here. This is going to remain as an aqueous situation, which means that both the sodium and the chlorine are going to become the spectator ions that we're going to ditch in our situation. So from an ion perspective, we get our hydrogen ions, we're going to get our carbonate ion or bicarbonate ion, and when that reaction takes place, we're going to get our water, and we're going to get our CO2 gas. And so really it didn't matter what type of an acid we used or what type of a carbonate bicarbonate that we used, the reaction was going to proceed the same way of getting our water, which is showing them the neutralization and making some CO2 gas, which would come off in this reaction. So that's kind of what we'd expect to see with this. I like to kind of make sure that we go back and let's do maybe a couple more of those pH calculations. So let's do at least one. So again, so we're getting used to seeing this little chart up here. And I've avoided doing this one because we can really just take this route, this route. So let's say we actually know the pH. Let's do a pH. So maybe I have the pH of a solution. So I know that I have a pH of, let's make it 8.7. Okay, now I know that this 8.7 is going to put me in a basic range. So this is a base. And I'm looking to know what is the concentration of the OH ions. Because maybe this is some kind of maybe it's like a calcium carbonate. No, yeah, let's do a calcium hydroxide. Okay, so I have a solution of calcium hydroxide. I want to know I know that the pH of the solution is this, and I want to know what is the concentration of the OH. Now, what we're going to do here is we're going to take that path where if I know the pH, okay, I'm going to go ahead and I'm going to figure out what my POH is, and then I'm going to go back here to figure out the concentration of my hydroxide. So, first of all, I know that POH is equal to 14 minus the pH. So I'm going to grab a calculator here to do a 14 minus our 8.7. And I know that I get a POH of 5.3. Now what I want to do is I want to use that to figure out what the concentrations of the hydroxide. So we go 10 to the negative 5.3 is what I'm going to get my hydroxide ion concentration. So I'm going to go ahead and get onto my scientific mode. I'm going to take my 5.3 negative, I'm going to press that 10 to the, and so I know that I'm getting a 5.0 times 10 to the 1, 2, 3, 4, 5, 6, negative 6 OH, molarity of the OH ions. Okay. Now, if we looked at that calcium hydroxide, we could go one step further here with this. Let's say we have our calcium hydroxide, and we know that as a compound, calcium hydroxide will dissociate to form calcium ions, and it'll form hydroxide ions. Now, if I really wanted to figure out what was the concentration of the original solution, I know that I have my hydroxide ion concentration, and that the concentration here is twice whatever the concentration is of the base. So I'm going to take that 5.0 times 10 to the negative 6 molarity, and really what I'm doing is I'm saying that 2 of these will produce 1 of those in a mole to mole fashion. And so really, if I cut this in half, I would know the original concentration. So I'm just going to do that now. So I'm going to take this and divide it by 2. And so my 2.5 times 10 to the negative 1, 2, 3, 4, 5, 6 molarity CaOH2. Now the same would work if I wanted to start with adding some calcium hydroxide into my solution, and then I could figure out what the concentration would be of that, and then I'd be able to go back and do it the other way as well. So we're starting to kind of tie in that concept of what we do with stoichiometry into looking at the concentrations of various substances, depending upon how many ions are produced within that species. We will go over video 3 tomorrow, where we'll look a little bit more at those reactions and those titrations, and we'll look at how stoichiometry really connects with this.